Today we are going to continue with the following chapters, which is on magnetic properties. Some of material produced in material industry can actually exist as magnetic materials. Okay, so in this chapter we are going to measure the magnetic properties. And what are the atomic reasons for magnetism? How does the materials can exist as magnetic materials? How are magnetic materials are being classified? So you have different types of diamagnetic, paramagnetics, ferromagnetics, ferric magnetics, and whatsoever. And materials designed for magnetic storage. Magnetic storage have been used for various kinds of application. For examples like for speakers, bell, and whatsoever. So all these actually need the so-called magnetic storage properties. And finally, the importance of superconducting magnets. Superconducting, or I think people have coined the word magnetic levitation or maglev technology. So you've seen this a lot in speed trains. I guess maybe later on we are going to see the examples, and you will understand how does the speed train actually can have a very high speed limit. So first of all, we need to understand the definition of magnetism. Sifat kemagnetan. Okay, magnetism is the phenomenon by which material exerts an attractive or repulsive force or influence on other materials. You know that for magnets, you learned it in physics as well, Form 4 or Form 5. Okay, magnet have different, I think, force. It can be attractive, it can be repulsive as well. If it is actually attracted with different different poles, you have a north and south, this can actually give attraction. But if it is faced with each other the same pole, then what happens is the repulsive force. Magnetic force is actually generated by moving electrically charged particles. So this magnetic force are been in addition to any electrostatic force that may prevail. Okay, you've seen magnetic bars, you've seen magnetic, I think, coin or whatsoever. But did you know that you can actually produce magnetic force by just having a coil wire? So if you have a coil wire, okay, and you put current flow on it, so what happens is actually it will generate a so-called magnetic force because you have an electrically charged particles that resulted from a moving of current. So this is actually in relation also with our previous chapters on electrical properties. Since every material consists of atoms, atoms consist of charged electrons spinning around them, similar to a current carrying a loop that generates a magnetic field. Thus, every material possesses a certain degree of magnetic force. So some material, it has a spinning, electron spinning around them. Okay, so this actually creates, I think, properties where some materials can exist as a permanent magnet or temporary magnet. I'm sorry, I hear some background. Adila, can you mute your mic? Okay, thank you very much. Right. So magnetic behavior of materials is determined primarily by electronic structure of a material and can be controlled by its composition, microstructure, and processing of basic materials. The manner in which a material responds to a magnetic field is scale, which determines whether the material will be strongly or weakly magnetic materials. So this, I think, behavior that produce from the magnetic field response can determine whether the materials produced will have a strong magnetic properties or a very weak magnetic properties. So as I said earlier, magnetic field is a force which is generated due to the energy change in the volume of space. Magnetic field is produced by electrically charged in motion. For example, a current flowing in the conductors, so orbital movement and spinning of electron will produce. And magnetic field can be described by imaginary line as shown in figure below for a magnet and a current loop. If you still remember, there's also one experiment, okay, in physics where you have a magnet bars, okay, and you put on top a piece of paper, and I think you just sprinkle iron dust on top. So what you can see is that you can actually see the magnetic lines or the force of magnets. Okay, so this actually tells you, even though we cannot see visually the magnetic lines or the force, but this can give you some indication how does magnetic field is being generated. And I said earlier that you can also produce your magnets by having a device. Like for example, over here, you can produce a magnetic field when you have a coil of wire. Okay, and when you actually put some current that flows into this spirally coiled wire, then it will actually produce a so-called applied magnetic field, or H. Okay, and the applied magnetic field created by a current through a coil can be actually related with the number of the total turns and also the length of each turn. Therefore, the magnetic field, the applied magnetic field, H, is equals to the number of turns multiplied with the current over the length. And magnetic induction results by the materials, or sometimes we call it as B. The magnetic induction is actually as a result of the magnetic field produced, okay, from the applied current. So when you have the apply or the moment of magnetic field, so what happens is that it will actually create a so-called induction effect. So this magnetic induction have a unit of Tesla, okay, and obviously from the unit itself, you know that the magnetic induction has been well explained by Tesla. And we also have a so-called magnetic susceptibility. Okay, so magnetic susceptibility actually measures the material response relatively to a vacuum. Okay, so you can actually have a phenomenon where the magnetic susceptibility can be equal to 0 if it is in vacuum. And you can also have magnetic susceptibility that is lower than 0 and higher than 0. So all this actually going to be related with the types of magnets that we are going to look in the next subchapter. Magnetic field strength. If a magnetic field H is generated by a cylindrical coil or solenoid of N turns and also length L, so we know that applied magnetic field H is equals to N multiplied with current over the length. Magnetic flux density or induction B, it is the magnitude of the field strength within a substance subjected to the field H. Okay? So B can be calculated as mu multiplied with H. Okay, and mu is actually the so-called permeability, permeability in a vacuum. Okay, it is measured of a degree to which a material can be magnetized in a vacuum. Okay, the magnetic flux density or the induction is equals to mu naught multiplied with H, where mu naught is the permeability of a vacuum, and it is a universal constant where value is equals to 4 pi times 10 power of minus 7. Okay? And mu r is basically the relative permeability and can be calculated by mu over mu naught, where mu is obviously permeability over the permeability in a vacuum. Magnetic susceptibility X, it measures the response of electrons to a magnetic field. Okay, electron produce magnetic moments when you have a spinning of electrons. Okay, so the spinning of electron creates the so-called magnetic moments, and then the net of magnetic moment can be the sum of the moment from all electrons. Okay, and there are three types of response that we are going to look at later after this. And the magnetization, it means that with the application of magnetic field, magnet moments in the material tends to align and thus increase the magnitudes of the field strength. So what does it mean by this statement? It means that you have a material that has a magnetic moment, but the alignment is not really in order. It's a bit random. So when you apply the magnetic field, when you apply magnetic field to this permanent magnet, what happens is that it will actually align the moment, and this will give, I think, a more strength to the materials to have a magnetic properties. So this phenomenon is called magnetization. Okay, thus increase in given by the parameter called magnetization M, that later on, if we relate with the induction formula, B is equal to mu naught multiplied with H plus with mu naught multiplied with M. So M is actually magnetization, that equals to the magnetic susceptibility X multiplied with H. Okay, and magnetic susceptibility can be calculated by relative permeability minus with 1. Okay, so as I said earlier, okay, for magnetic susceptibility, there's three types that we can see, the three types of response. Depending on the existence and alignment of magnetic moments with or without application of magnetic field, there are three types of magnetism that can be defined. So in magnetism, you have the first one is so-called diamagnetism, paramagnetism, and ferromagnetism. So I really hope that you guys understand the definition and also the differences between all these types of magnetism. Because I think in this chapter, it is clear that we are going to study the different properties of these magnetism materials. And then I think normally in exams, the types of question that you are being asked is to differentiate or to discuss the behavior of all these three different types of magnetism. But I think later on we will see different anti-ferromagnetism and whatsoever. So classification of magnetic materials. All materials can be classified in terms of their magnetic behavior, falling into one of four categories, depending of their bulk magnetic susceptibility. So as you can see over here, in the periodic table, we can actually classify the materials depending on their magnetic properties. Of course, for materials that having properties of gas, it is clear that this this material is not non-magnetic material. So clearly, diamagnetic, it means that materials that doesn't exist as magnets. Materials which is not magnet or not having a magnetic properties. Okay. So examples. So we can see that gases or some maybe hydrocarbon. Okay, and some other things. So all these are actually diamagnetism because it doesn't have any magnetic moments. It doesn't have any permanent magnet properties. Okay, so obviously you can see from here that diamagnetism for noble gas, all these are actually dimagnets. And some materials that is a hydrocarbon, like this one is also non-magnets. Okay, and even some metals is also exist as diamagnetic materials as well. Some metals also exist as diamagnetic materials, like for example gold and silver. Okay, Gold and silver is also not having a permanent magnets or magnetic properties. Okay, so this is why if you check, it didn't actually interact with magnets. Mercury, indium, and other types, lead and others, is also not having magnetic properties. So the one that doesn't exist as magnetic property is known as diamagnetism. Paramagnetism, I think later on you will see that it means that this material exists slightly a moment. It has a magnetic properties, but only it will become magnets if you apply magnetism. If you apply external magnetic field, then it will become magnets. But originally itself, it doesn't having any attraction or repulsive properties. But if you apply magnetic field, then what happens is that it can be magnets. So this actually what does it mean by ferromagnetics? Paramagnetics. Ferromagnet and also antiferro, it means that materials that have a configuration of iron or ferro magnets. Of course, this one have magnetic properties. And anti-ferromagnetism, it is actually in opposite to the ferromagnetics properties. Okay. So we are going to look into one by one. So for diamagnetism, it is a weak form of magnetism which arises only when an external field is applied. It arises due to the change in orbital motion of electron on application of magnetic field. There is no magnetic dipoles in absence of magnetic field, and when magnetic field is applied, the dipole moments are aligned, okay, opposite to the direction, to the field direction. The magnetic susceptibility is negative. So it means that X is equals to less than 0. And magnetic induction, B, in a diamagnetic material is less than that of in the vacuum. Part of the examples of diamagnetic materials is aluminum oxide, copper, gold, silicon, and also zinc. So as I said earlier, okay, how to define diamagnetism? It is actually a weak form of magnetism. We know that it doesn't exist as magnet in initial stage. This is actually initial stage and final stage. Final means that when you apply a so-called external magnetic field. So here, H is equal to 0. No magnetic field is applied. So you didn't see any dipole, or you didn't see any moment on this, I think, magnetic structure. But when you apply external force, what you can see is that it will produce a moment, magnetic moment, but it will be opposite to the direction of magnetic field. Okay, right. So in the end of the day, I guess in order to discuss diamagnetism, you need to draw this one. Okay, you need to draw to differentiate what happened. I think initially when there is no, or H is equal to 0, and what happened to the magnetic properties when H is applied. So H is applied, there's a moment produced, but it is actually, I think, in opposite to the direction of the magnetic field. So obviously this doesn't give any net. Net is equal to 0. Then obviously there is no magnet attraction or magnetic properties. Okay. And other than that, I guess X is less than 0. Okay. And B, the induction in a diamagnetic properties is less than in a vacuum. So a few points that you need to remember is diamagnetism. It means that it is a weak form of magnetism. Okay, so you need to show, I think, the difference in initial state when there is no applied magnetic field, there's no moment, and when you put some external magnetic field, it will be in opposite. Okay, and magnetic susceptibility is equal to 0. So at least you already have like 1, 2, 3 points, okay, to define the diamagnetic properties, diamagnetism. Okay, so moving on to the next one, paramagnetism. In a paramagnetism materials, the cancellation of magnetic moments between the electron pair is incomplete, and hence magnetic moments exist without an external magnetic field. However, the magnetic moments are randomly aligned and hence no magnetization without any external field. When a magnetic field is applied, all the dipole moments are aligned in direction of the field. The magnetic susceptibility is small but positive. Okay. The induction in paramagnetic is slightly greater than that of in vacuum. Okay. So, as I told you earlier, that paramagnetism it has a moment, but it doesn't exert or give any magnetic properties initially when there is no applied or external magnetic field, because you can see over here, okay, that the moment is actually random arrangement, which results cancellation of magnetic moments. Okay, because you have a very random. So in the end of the day, it will be, I think, the overall moments will be cancelled off. Okay, but what happens if you apply external magnetic field? All these moments will be aligned. Okay, it will be aligned, and the direction will follows to the direction of external magnetic field. Okay, so X is positive, greater than 0, but it is small. Okay, right? And some examples of paramagnetic materials could be aluminium, chromium, molybdenum, titanium, and zirconium. So all these are actually examples of paramagnetism materials. Okay. Ferromagnetics. Okay. So ferromagnets, certain materials possess permanent magnetic moments in the absence of an external magnetic field. So this is known as ferromagnets. Okay. So ferromagnets, as I said earlier, it contains or possesses permanent magnetic field. Obviously, this magnet can attracted to magnets, easily attracted to magnets. The best example is iron, because if you put magnets and you put iron, it will be attracted. Okay. All right. So permanent magnets moment in ferromagnetic materials arises due to uncancellation of electron spin by virtue of their electron structure. The coupling interaction of electron spin of adjacent atoms causes alignment of moments with one another. The original of this coupling is attributed to the electron structure. Okay? Ferromagnetic materials like iron that has a proton number of 26. So if you put the electron configuration, you will have like a configuration which equals to argon 4s2 3d6, have incomplete d orbitals, okay, and hence unpaired electron spin. So we know that d orbital it should have 10. So the one over here you only have 6. So that is why you have unpaired electron spin. Okay, right. So for anti-ferromagnetism, if the coupling of electron spin results in anti-parallel alignment, okay, then the spin will cancel each other, and there will be no net of magnetic moment will arise. So this is obviously known as anti-ferromagnetism. Magnesium oxide is one such example. In manganese oxide, okay, the oxide ions have no magnetic moments and have the spin moment of manganese ion, which align anti-parallel to each another in adjacent atom. Okay, right. So in this case, antiferromagnetism could be, I think, produced from normally metal oxides. Okay, right. So for oxides or oxygen, normally this is actually dimagnetics. Okay, and magnesium, it is actually considered as paramagnet. So when you have a combination between manganese and also oxide, so the arrangement is actually alternating with each other. So that is why it is, resulted a cancellation because of the, I think the moment aligned is anti to the direction of a ferromagnetism. Because of ferromagnetism, you will have, sorry, I think maybe this one I didn't show you how does this dipole arrangement. Okay, in ferromagnetism, you will have something like this. It is not really straight, but the direction is actually going to one side. Can you see? H is equal to 0. But obviously, because of the direction is at one side, it still have these permanent magnet properties. So when H is applied, you will see that the alignment will be more definite. Okay, so this is actually for ferromagnetism. For anti-ferromagnetism, so you see that this one, it has alternating, I think, arrangement of dimagnets, paramagnets and dimagnets. So it will result in so-called anti-ferromagnetism properties because the alignment is actually not straight. So obviously, anti-ferromagnetism doesn't have any, magnetic properties. No magnet properties. Okay, ferromagnetism, you know that this one, it has a permanent magnet properties. Okay, meanwhile for this one, there is no permanent magnet properties. Okay, right. And lastly, we have a so-called ferrimagnetism. Ferrimagnetism, because of the oxidation state of iron, if it is ferro, then 2 plus. Ferri, it means that it has 3 plus. Certain iron solids, having a general formula of M Fe2O4, where M is any metal, show permanent magnetisms, termed ferrimagnetisms, due to partial cancellation of spin moments. For example, if you have magnetite, or Fe3O4, this is actually magnetite. So M is equal to Fe plus Fe2, then become Fe3O4. Fe can exist in both 2 plus and 3 plus states as Fe2 plus, okay, and also Fe3 plus in the ratio of 1 to 2. The anti-parallel coupling between Fe3, half A sides and half B sides moment cancels each other. Fe2 moments are aligned in the same direction and results a net in magnetic moments. So ferrimagnetism actually have permanent magnets properties. But it's just that I think the arrangement is slightly different as compared to ferrimagnetism. Okay, but still it gives permanent magnetism properties. So in order to identify ferrimagnetism, the general formula is basically M Fe2O4. Okay, and the best example is this one, magnetite, Fe3O4. All right. Okay. So how do we compare the magnetic susceptibility of all these different types of magnetism? So as I can see, the first one, diamagnetic. Diamagnetic, we know that the magnetic susceptibility is always lower than 0. Okay, and you will see that the response between the magnetic induction to the magnetic field, it is always at the lowest. So when you have an indicator of magnetic susceptibility at 0, Paramagnetic is slightly positive but small, and for ferro and ferric magnets, the magnetic susceptibility is quite large. Okay, so this one more than 0 and large, as compared to um, paramagnets. Right. So this is actually a very straightforward or a very much important um, figure to show the difference between dimagnetics, paramagnetics, and ferromagnetics property. As I said earlier, when there is no magnetic field, for dimagnetics, you don't have any moment. When you apply magnetic field, there is moment produced, but it is actually opposing to the magnetic field direction. Paramagnets, it has a random moment, and when you apply magnetic field, all this moment will be aligned, follow to the same direction of magnetic field. And finally, for ferro and ferrimagnetics material, it has an aligned moment, one direction. And when you actually apply magnetic field H, I think the alignment will be more aligned, okay, as compared to the initial. But obviously for ferro and ferrimagnetics, it has these permanent magnet properties because it already have these aligned moments, okay, even without magnetic field application. All right. So I just want to check is there is any question from you guys regarding on the different types of magnetism that we have looked so far before we move on. Okay, magnetic domains. So domain is actually means that the different, I think, clusters that shows the direction or the moment of magnets. Ferromagnetic materials exhibit a small volume region in which magnetic moments are aligned in the same direction. So these regions are called domains. Adjacent domains are separated by domains boundary. The direction of magnetization changes across the boundaries, and the magnitude of magnetization in the material is vector sum of magnetization of all these domains. So basically what we just want to see is that you don't see this kind of arrangement. We don't see this kind of arrangement in, I think, in a material. But normally what you can see is like this. Okay, it will be the small circle is actually represents as this. Okay, imagine that you have a metal. You know that each metal, for example, if it is a alloy or a metallic compound, then all these metallic compound will have different phase. So the domain is actually like that. It has like each phase will have a different domain, will be equal to a domain, and each phase or domains will have different movement. Okay, so I think that is why I think towards the end, if you apply H, so what you can see is that later on, for this, the whole thing of domain, it will be one direction lah. This is just to explain you lah. Because earlier we look into this, I think, configuration or these drawings, but in reality, the moment is actually been put in the domain. So this domain is actually represents or separated by a domain wall, and to create a structure. Right. So if you still remember, what does it mean by magnetization? Magnetization, it means that you put some external magnetic field into your material, which can increase the properties of the magnets. Initially for paramagnets, the moment is random, but when you apply, I think, external magnetic field, or so-called magnetization process, so what happens is that the moment will be aligned, and finally it become a permanent magnet. Okay. So when a magnetic field is applied to a ferromagnetic materials, domain tends to align in the direction of the field by domain boundaries, movement, and hence the flux density or magnetization will be increased. As the field strength increases, domain which are favorably oriented to the field direction grow at the expense of the unfavorably oriented one. All the domains are aligned to the field direction at high field strength, and the material reaches the saturation magnetization, or so-called MS. Okay, all right. So you can see that from this plot, um, induction, magnetic induction or magnetization versus applied magnetic field. Initially at zero, you have this moment. Okay, you have a random moment for paramagnets, or maybe for ferro magnets. So when you increase, when you start to apply a magnetic field, so what happens is that the moment is start to align, okay, align, and finally it will show one direction. So when it show one direction, this where we call it, it achieve a so-called saturation state. Okay, so this is actually considered where permanent magnets will behave. Okay, all right. So as you can see from this ferro and ferrimagnetic materials, as you increase, okay, the applied field, the magnetic moments will be aligned with each direction. Okay, so you'll see that the moment for each domain is start to reorganize, and finally it forms one uniform movement. Okay, all right. So the plot for I think magnetic induction to the applied magnetic field is obviously like exponential curve, exponent curve. You have an increase and finally become flat. Okay, so this is actually where the magnetization occurs. Okay, right. So is there any possibilities where magnetization will be released, or we call it as we stop the magnetization after it reaches saturation? We stop the how to say the applied magnetic field. Do you think that the material will exist back? I mean, as initial? The answer will be from this hysteresis. Hysteresis will be produced, okay, as a result when the materials doesn't behave as the initial magnetic properties. Okay, so you can see from here, this is actually induction versus applied potential. Okay, when you increase applied magnetic field, what happens is that the moment from each domain will be aligned, and this is where magnetization occurs. Okay, until it reaches saturation. Right. As I said, what happens if you stop? Okay? If you stop the applied potential, okay? If you stop the applied potential, it will result a so-called coercivity. Okay? Coercivity happens when a reverse field strength is produced as a result of zero magnetism. Okay? So that is why over here you will see that it goes up, and then after you stop the applied magnetic field, so-called coercivity will happen. H is equal to 0 back, but you didn't see that it goes back into the initial state. It's just dropped back to a more negative or a more positive state. So it means that when you apply external magnetic field, I think theoretically the dipole moment will be slightly changed. Macam orang kena electric lah. So when you put some external force, do you think that it still will behave as normal back? Okay, obviously no. Okay, so you have a permanent effect. Okay, when it reach a permanent magnet's properties after the applied magnetic field is being produced, then there will be some effects to the dipole or to the moment of each material. So that is why when you stop the magnetization or magnetization is equal to 0, you see that the profile of this is not going to be similar as initial. It will go to slightly more negative or slightly more positive. And this effect is known to be coercivity. If the field is reduced from saturation by magnetic reversal, a hysteresis will develop. Okay, as the field is reversed, the fabulally oriented domain tends to align in the new direction. Okay, when H reaches 0, some of the domain still remain aligned in the previous direction, giving rise to a residual magnetization that calls remanence. Okay, so remanence is basically here. This is actually the values overlapping. I mean, at H is equal to 0, then you get the initial value is not equals to 0. So you have some offset values, which is known to be MR. So MR is actually remanence. So if I said offset, maybe you can remember back from your mechanical properties. When you have elastic and then plastic, plastic means permanent. When you release back the force, what happens is that it didn't go back to the initial shape. It has a permanent damage. So similar for magnets as well. So when you apply magnetic field, external magnetic field, because it's a force, a type of force. So when you stop, there will be some permanent effect to the magnets. So what happened is that it didn't produce the same, properties as before, and it has some offset. For magnets, it's called remanence. Okay. All right. Okay. So very quickly, hard and soft magnets. Okay. So to differentiate hard and soft magnets, hard magnets is normally produced if you have materials that having a permanent magnets, a very strong permanent magnets properties. Okay. And therefore, the hysteresis is slightly bigger as compared to soft magnet. Soft magnet is actually materials that exist a temporary magnetic properties. So obviously for soft magnets, it will have a narrow hysteresis curve as compared to hard magnets. Okay, because I think the remanence or the coercivity profile is very much different between all these materials. So normally for hard magnets, the best example is for ferro and also ferric magnets. Okay. For soft magnets, this could be for paramagnetic materials. Right? The magnetic hardness is expressed by the term called energy products, in which the area of the largest rectangle can be drawn as the second quadrant. Conventional hard magnets like steel, knife, okay, alloys, alnico alloys have the induction to applied magnetic field values in the range of 2 to 80. Higher energy hard magnets materials like this example will, the ND2Fe14B and others can exist induction to applied magnetic fields greater than 80 kilojoule over magnetic cube. Meter cube. Hard magnets are used in permanent magnets in applications such as power drills, okay, motors and speaker. Soft magnets like iron are useful when rapid magnetization and demagnetization is required, as in transformer's core. Impurity in other defects should be low for this purpose, as they may hinder the domain wall movement through which the domain will align. Okay, so you can see the permanent magnets. I mean, the comparison between the process of hard magnets and soft magnets. For soft magnet, it has a very narrow hysteresis. Okay, for hard magnet, it has a very huge hysteresis, I think, loop due to a larger coercivity. Okay, so for magnetic storage, obviously, okay, this for the application of different types of magnets. Information can be stored in magnetic materials. For example, hard disk drive. So hard disk drive, it has properties where it can store the information or store the I think the dipole moments. So applied magnetic field H and the alignment of domains. This is where the magnetization of materials can be formed, and it can detect a small change in the magnetization of the medium. Okay, so of course there's two types of media for magnetic storage. You can have particulates and you can have also thin film. All these are just examples. I guess for magnetic storage, what you just need to understand is that magnetic properties or materials that has a magnetic properties can also have these magnetic storage properties where it can store information. Okay, because of it has a permanent magnets, a permanent dipoles, which allow them to store all this information and after that release the information back. Okay, I guess for superconductivity, we can continue this in our next lecture. I think maybe for my offline lectures tomorrow, I'm going to cover superconductivity before moving on to the next chapter on thermal properties. Okay, and after that, maybe we'll going to finish with magnetic properties. I think chapter, right? So before I end lectures for today, is there any questions so far? Anything? Right? So for your quiz, I think your quiz, I'm going to give you your quiz on Wednesday, right? So it will be covered for electrical properties and also magnetic properties. And of course, the same as before, I will stay back for a few minutes to answer any of your question. Okay, I saw there's one question asking when is final exam. It has not been decided by the school yet, so don't worry. I still will let you know the date. Okay. So any other question apart from that, I'm happy to answer. We'll stay back. So if you guys doesn't have any questions, so thank you very much. So we'll see you in the pre-recorded lecture tomorrow. I will post it in the in the YouTube. I will let you guys know, and we'll see back live on Wednesday. So with that, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.